Hey Hires, so today what we're going to do, we're going to start a new topic which is all about fats and oils. There's no starter today, that will come with the next lesson, so we're just going to jump straight in. So make sure you've got a pen, paper, and you've got the heading fats and oils. Okay, so we're going to start off and talk about natural fats and oils. So natural fats have animal origins. Okay, so all our natural fats are coming from animals essentially. Yeah. Natural oils, however, have vegetable and marine. Okay, so fish essentially. Vegetable and marine origins. Okay, so vegetable, you're talking about plants, stuff like that. Marine, talking about fish. So, for example, yeah, this bit isn't really important, it's just giving you an example of where we would find fats and oils. So, we'll go for the fats first. Let's go for suet. You might have got some suet in your cupboards. We get that from cows and sheep. Yeah. Lard you'll get from pigs. So that there, that's your animal ones. I'll go for sunflower oil. You get them from, quite obviously, sunflowers. And cod liver oil, funny enough, you get them from cod. Okay, so that's your vegetable one, and that is your marine one. Okay, so can you see that? Yep. So fats and oils, you probably already know this, in fact you will know this, are an essential part of the diet. Okay, they provide the body with energy. Yeah, that's why we're eating fat. Provide the body with energy, and they are a more concentrated source of energy than carbohydrates. Okay. Now, we've also got another sort of function, so they are also essential for the transport and storage of fat soluble vitamins in the body. Okay, so you need to know the two sort of functions of the fats and oils and why we eat them. So provide the body with energy, and they're essential for the transport and storage of fat soluble vitamins. Okay. Right, now let's look at the structure. Yeah, what they're made up of. So the structure of them. Now, the good thing about fats and oils is that you guys already know what they are. You should be able to recognise the homologacies. So fats and oils are esters. Okay, and in the case of a fat and an oil, this is called a triglyceride. Okay, so fats and oils are esters, and you'll understand why it's triglyceride just now, but don't worry too much about that. So fats and oils are esters and are made up from glycerol, okay, which we've spoke about before. It was even in your December assessment, made up of glycerol, which is an alcohol, yeah, made up from glycerol and 3 fatty acids, okay, and fatty acids simply are just long chained carboxylic acids, okay, and it makes sense because fats and oils are esters, and you should know from the previous topic that esters are made up of an alcohol and a carboxylic acid. Yeah? Right, so what we're going to do before we start looking properly at the structure of a fat and an oil, we're going to look at what glycerol is, just a wee recap, and what a fatty acid is. Okay, so we'll do glycerol first because we're familiar with that, or should be. So glycerol looks like this. It's got 3 carbons, and each carbon has an OH attached to it. Now I'm going to do this, you're going to see how I'm going to do this. I'm going to do an OH up, I'm going to do an OH down, and then I'm going to do another OH up, okay? It doesn't, if you get asked to draw glycerol, it won't matter how you do it, but you'll see why I'm doing it like this in a wee bit. Okay, so 3 hydroxyl groups, 3 carbons, each one attached to a carbon, that's your glycerol. Okay, and if you wanted the systematic name, again you should know how to do this. 3 carbons, so it's propane. You've got a hydroxyl group on carbon 1, 2 and 3, so it's propane 1, 2, 3, and because there's 3 of them, this is a triol. Okay, so propane 1, 2, 3, triol. Right. Next one is your fatty acid. Okay. Now fatty acid, again, like what I said earlier, it's literally just a carboxylic acid, but the difference between a fatty acid and just your normal methanoic, ethanoic, propanoic acids, it's a long chain. Okay, so usually we talk, when I'm talking about long chain, we're referring to maybe 15 carbons plus. Yeah, so you can get 15 carbons, maybe even 40 carbons. It's a long chain. Okay. For the purposes of this, so I'm not going to do 15, 17 carbons. I don't even think it would fit on my page. I'll see how many I can get on. Okay, so it would look something like this. So you've got your CH3, CH2. I'm not going to do the full, I'm just going to do the shortened structural formula. Just like that, okay? And because it's a carboxylic acid, it has the carboxyl functional group, okay? Which you should be familiar with. So how many carbons we got there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. Now usually, like I said, it's about 15 plus, but for the purposes of this it's fine. Now obviously if we go back to our structure, fats and oils are made up of glycerol and 3 fatty acids. Now I'm not going to write this out every single time, and I wouldn't expect you to be writing it out every single time. So what we can do is we can shorten it, okay? And you will have seen this before, but I'll draw it again anyway. Okay, so that's a shorthand way of drawing a fatty acid where every point represents a carbon. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, I'll maybe just take one away. Take that one away. Okay, so every point equals a carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so that's a shorthand way of writing it, and you may be asked to draw a sort of fat and an oil, and you don't want to be drawing the CH3, CH2, CH2 all the time, so I would always recommend that you do that. In fact, yes, do that. Okay, now what we're going to do, we're going to look at the reaction. Okay, again, this is something you're familiar with. I'm not teaching any new reactions here, I'm just applying it to glycerol and 3 fatty acids. Okay, so make a wee note about this. So fats and oils are made from condensation reactions. Okay, and again that should make sense because fats and oils are esters, yeah, triglycerides. So esters are made from condensation reactions. Now be careful here, you wouldn't call this reaction an esterification. When we're talking about esterification, we're talking about the esters that we would make for like perfume. Sorry, that's my cat. Vanderbilt, if you've ever heard me speak about them. So fats and oils are made from condensation reactions. Sorry, where was it? Like I was saying, you couldn't really say esterification here. When we talk about esterification, it's usually talking about esters that are made, the ones that we'd use for like perfumes, flavourings, stuff like that. Okay, so fats and oils are made from condensation reactions, and I'm going to highlight that. Yeah, condensation reactions. So let's show how this works then. So what we have, what I'm going to do is I'm going to take my glycerol, okay, and I'm going to turn it on its side, and you'll see why I drew glycerol like this last time. Remember I had 2 OHs on one side and then 1 OH on that side. This is because this is the structure of fats and oils, yeah, and I'll talk about that once we get to it. Obviously put in your carbons, your hydrogens, don't forget, and for each hydroxyl group, yeah, we're going to line up fatty acid. So remember, you've got the functional group, you've got the carboxyl group, and then you've got the long chain. Now, when you're drawing this, it doesn't matter how many you've got, as long as you've got a relatively long chain, okay? So I'm going to do that for each one, like so. And you guys, you'll need to practice this. You'll need to practice how to draw the long chain fatty acids. Okay, now they don't all have to be the same size, you can mix and match. Again, it doesn't matter at this point. What's important is the reaction. Now, this is easy because you've already done it before. Remember when you're talking about esters, you get the removal, the elimination of water. So you get the H, you get the H from the glycerol, you get the OH from the carboxyl group. Okay, and again, what happens there, if I take a different pen, is that O will combine there. Okay, and that happens for every single one. You get the OH from the carboxyl, you get the H from the alcohol, like that. Yeah, and you get that sort of formation. Now, if I now draw that again, I will draw my glycerol in. And I would then draw my rest of the molecule. Okay, so it looks like that. Again, what you should notice, okay, because we're making a fat and an oil, we've combined an alcohol and a carboxylic acid, we've made an ester, so what we've got is we've got 3 ester links here, okay, and that is why it's called a triglyceride, okay, because we've got 3 ester links. And that's your fat and oil. Yeah. Now, obviously, because it is a condensation reaction, we've eliminated the water 3 times. You do need to write that. So that's 3 moles of H2O. And that's it. Yeah. How easy is that? Okay. But you need to practice it. Okay. You can't just watch it once and have it memorized. You need to practice. You need to practice it. Okay. But maybe if I just go back to this. Okay. So essentially, what you need to know is that you've got glycerol, and coming off the glycerol you've got a fatty acid, and you have 3 of them. Okay, so that's what it should look like. It's sort of that shape you're after. I don't know if you've seen like the old tuning forks, kind of look like that. Okay, or what my other higher class said last year, kind of looks like a glass of wine, I suppose. Right, now, so we'll make a wee extra note here. So fats and oils are made from, I know we've already said this, but you'll see why I'm doing this, are made from glycerol and fatty acids in the ratio of 1 to 3. And you can get asked that quite a lot actually. Okay, it's a 1 to 3 ratio. 1 molecule of glycerol and you've got 3 fatty acids. Yeah, so make sure you know that. Yeah, 1 glycerol, 3 fatty acids. That's so important. Yeah, and obviously I suppose you could call this a wee summary. Okay, the type of reaction is a condensation reaction because we're making esters. Yeah, a lot of people, when it comes to tests in the future, they forget that fats and oils are esters. They're triglycerides because they're containing 3 ester links. Okay, and you've got that tuning fork glass of wine shape. Now, what I'm going to do now is I'm going to separate them. I've spoken about fats and oils together, okay? Now, they're both made up of 3 fatty acids, they're both made up of glycerol, but they are different. Yeah, they do have a sort of massive difference. And we'll talk about that, okay? So we're going to look at the properties of fats and oils. Yeah. Now, if you look at your common fats, we spoke about lard, butter is a type of fat, stuff like that. Okay, so fats at room temperature are solids. Yeah. Now, oils, okay, pretty straightforward. This oils at room temp are liquids. Okay. So that's the major difference between the two, solids and liquids. So as chemists, we need to work out why that is. Why are fats solids? Why are oils liquids? And it all comes back to the bonding, okay, the intermolecular forces. Everything comes back really to bonding. So the good thing is, as I'm teaching this, there aren't really any new concepts I'm going to introduce, okay, so it's all stuff that you're familiar with. We're just going to look at them, okay. Now, let's look at fats, okay, and then we'll do the same for oils. So we'll look at fats and we'll work out why they are solids, okay. So fats are saturated molecules, okay. Now that word you probably haven't heard since Nat 5, okay. So what that means is fats are saturated molecules, contain only carbon to carbon single bonds, okay. There are no carbon to carbon, oh sorry I moved that over. There are no carbon to carbon double bonds, they're only single bonds, okay. So due to this, fats have a higher melting point compared to oils, okay. So I'm going to show you what I'm going to show you what happens. So if we look at fat, okay. Now I'm going to simplify this. I'm not going to draw it out. I'm not going to draw the ester lengths. I'm not going to draw the carbons, anything like that. I'm going to do the structure that looks like this. Okay, so that there is our long chain fatty acid, and this line here is going to represent the glycerol. Okay, if we go back to this molecule here, 3 carbons in a row, that's going to be your glycerol. And again, we've got that tuning fork structure. And it looks like that. Yeah, does that make sense? Now, carbon to carbon single bonds give a linear shape. Yeah, and you can see that even though obviously they're going zigzagging, the general shape, it is going in a line. It's a linear structure. Yeah, each sort of fatty acid chain is a linear shape. Okay, so carbon to carbon single bonds give a linear shape. And this is the cool part. This allows other fat molecules to closely pack. Sorry, I'm going to sneeze. No, I'm not. This allows other fat molecules to closely pack together. Okay, now if I'm going to draw this on a different pen just so you can see clearly. If I was to draw another fat molecule, okay, I would have the fatty acid chain in here. I've got my glycerol, I've got my other one like that, and it looks like that. Okay, so what that allows, it allows the fat molecules, they're packing close together like that. Yeah, they're close, so close together, nice and snug like that. And if we were to get another one, do this in a different pen. Yeah, again you can see they're closely packed together like that. Okay, now so due to this, the LDFs, because again remember these are just carbon hydrogen. Okay, so because obviously the electronegativity is less than 0.5, it's non-polar, they only contain LDFs, okay? But because they're closely packed together like this, yeah, the LDFs are stronger, okay? And again, you should know if we've got stronger LDFs, they're harder to break, and that gives them a higher melting point, okay? So due to this, the LDFs are stronger, and due to this, LDFs are stronger, and harder to break. Therefore, they've got a higher melting point. And that's it. That's why fats are solid, because of this close packing due to the saturation. Okay, due to fats being saturated, and that's so key. Yeah, because they're saturated, that gives the fat a linear shape. Okay, and that linear shape allows the molecules to closely pack together, and then that makes the LDFs, they're going to be stronger, harder to break, and that's why you've got a higher melting point. Okay. So what we're going to do now, we're going to look at oils. Okay. Now, this is straightforward. Now, once you've got the fats, the oils are relatively straightforward. Okay, so fats are saturated, so obviously oils are going to be unsaturated. And again, you need to know your definition of unsaturation, and that means it contains at least one carbon to carbon double bond. Okay. Don't say it contains a double bond, say it contains carbon to carbon double bond, because if we go back here, yeah, this is a double bond, but that molecule there is still saturated. Okay, it's only when it contains a carbon to carbon double bond does it become unsaturated. Okay, so oils are unsaturated molecules, contains at least one carbon to carbon double bond. Now this is the important part, because it contains a carbon to carbon double bond. What that does, this causes, there's a key word here, you want to say this causes kinks in the molecule. Okay, so because they're unsaturated, because they contain those carbon to carbon double bonds, this causes kinks in the molecule, in the molecules. Due to this, the oil molecules cannot pack closely together. Yeah. So due to this, the oil molecules cannot pack closely together. And I'm going to draw a wee diagram down here. Do leave a space, because we've got a wee bit more writing to do, not much, but just leave a space, maybe 4 or 5 lines. So what we have, if we take this line, that's our glycerol, yeah, 3 carbons, and what happens, this is our long chain, okay, at one point there's going to be a carbon to carbon double bond in there, okay, and the minute that happens, that causes the molecule to kink, okay, so it goes off in another direction, like that, yeah. So you've got your carbons, carbon to carbon double bond, and then that causes it to kink, and it goes off in another direction. And again, remember, you have 3 fatty acids. Okay, so every time you get a wee carbon to carbon double bond, you get a kink. Now you might get 2 in the fatty acid chain, yeah, so you get another one there, and that kinks off again. Just depends how many carbon to carbon double bonds you have. Now, because of this kink, it's so much harder, in fact it's nigh on impossible for them to closely pack. Now if I try and draw another one, I'll use a different pen. Let's just draw it here. Okay, so if I've got my straight chain, and then all of a sudden we've got a carbon to carbon double bond, that's causing it to kink, and it shoots off like that. And as you can see, they can no longer pack together. Kink because of the carbon to carbon double bond, kink because of the carbon to carbon double bond, and again they're unable to pack together. Like that. Okay, now obviously I'm not the best drawer in the world. You don't have to be, yeah, you just have to make it obvious that when there's a carbon to carbon double bond, there's a clear kink, it's went off in the opposite direction. And again, I'll use a different pen for this, go for bean. If we look at this, it might be best to go back to this one here. If we look at this, you'll see that you can get tons of LDFs. Yeah, the LDFs are becoming stronger because of this tightness. Like so. But if we look at the oil, you'll get some obviously, but you'll maybe get some there at a push, maybe there, but the further they get, you're not going to get any LDFs here. You're not going to get, you'll maybe get a wee bit there, but what I'm saying is you're not getting as many LDFs, so they're going to be weaker. Okay, so if we go back up here, so due to this, oil molecules cannot pack closely together. This causes the LDFs to get weaker and easier to break, therefore a lower melting point. Okay, and because it's got a lower melting point, that's why oils are like that. That's why oils are liquids. Okay, and that's so important. Now, you need to write that level of detail. There's no ifs and buts there. You need to write that, and if you accompany it with the drawing, that's even better. Okay, a typical exam type question would be explain why fats have a higher melting point than oils, or explain why fats are solids and oils are liquid at room temperature. It'll be worth 3 marks. This is the level of detail that we need. Okay, so it's all to do with the level of saturation. Fats are saturated, therefore contain only carbon to carbon single bonds. That causes no kinks, therefore they're going to closely pack together. Stronger LDFs, harder to break, higher melting point. And oils are exactly the opposite. They're unsaturated, they contain carbon to carbon double bonds. This causes kinks in the molecules, and those kinks don't allow them to pack close together. Okay, and because of that, you're going to get weaker LDFs, easier to break, lower melting point. Okay, so like I always say, you're never just going to hear this once and get it straight away. You need to go away, you need to practice it, you need to write it out, write it out, write it out, and get into that habit where you just memorise it. Okay, right, let's keep going. Now, just as a wee sort of side note, because this I've seen this come up in a past paper question before, and it's not in the active note. So, wee side note: fatty acids tend to have a bad / rancid smell. Yeah, rancid tends to be the word that you use, usually multiple choice questions, but yeah, fatty acids tend to have, oh sorry, that's a bad / rancid smell, a very horrible, disgusting smell. Okay, so that's how fats and oils are made. I'm going to do one more thing actually, and I think we'll stop there and we'll do some practice on it. So let's look at general formula for fatty acids. Okay, now remember what a lot of people do: fatty acids aren't fats and oils. Fats and oils are esters. Remember, fatty acids are long chained carboxylic acids. If I go, yeah, there you go. Okay, so fats and oils, remember, are made up of glycerol, propane 1,2,3 triol, and three long chained fatty acids. Okay, and then when three fatty acids react with glycerol, you get a fat or an oil. Okay, so try not to get all of them mixed up. Now fatty acids, yeah, just to remember, they are long chained carboxylic acids. Okay. And again, what's important about this is that they can be either saturated or unsaturated. Okay, and depending on what one they are, depends whether you get a fat or an oil. If we use saturated fatty acids, you're going to get a fat. If we use unsaturated fatty acids, you are going to get an oil. Okay, and that's because unsaturated fatty acids contain the carbon-to-carbon double bonds that causes kinks in the oil molecule. That doesn't allow oil molecules to pack together, weaker LDFs, easier to break, lower melting point, blah 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 blah. Okay, so depending on what type of fatty acid we use determines whether we get a fat or an oil. Now, I'm going to focus on saturated. Yeah. Now the general formula is exactly like the general formula for carboxylic acid. So actually you should already know this, but it is CnH2n plus 1 with the carboxyl group on it. Okay. So an example of a saturated fatty acid would be C15H31COOH, and that is what we call palmitic acid. Okay, now you don't need to know this off by heart, don't worry, I'm just showing you why this is saturated, because it follows the general formula. We've got 15 carbons, so N equals 15, so 2 times 15 is 30, plus 1, 31. So this here is a saturated fatty acid. Okay, and you can get asked this comes up all the time. Yeah, it's usually multiple choice questions. Don't worry, I will put up multiple choice questions for us to do. It's like starters and stuff like that. But yeah, that's it. Now, unsaturated. Now this is a wee bit harder because unsaturated, they don't have a general formula. Basically, it's when the formula isn't CnH2n plus 1 carboxyl group. So basically what we're saying here is that we will have, trying to think, so it will be when the hydrogens will be less than 2n plus 1. Okay, now that might not make sense just now, but let me get you an example of this. If we look at linoleic acid, okay, this has the general formula, this has the formula C17H31COOH. Now, if saturated, okay, the formula should be C17, and again if we sub that into our general formula there, C17, 2 times 17, 34, add 1, that should be 35, so H35 carboxyl group. However, it isn't, it's C17H31, so because the hydrogens are less than 35, we can confidently say this is unsaturated, yeah, because it contains a carbon to carbon double bond. Now I know just by, you guys might be able to work this out as well, but I know just by looking at this, this actually contains 2 carbon to carbon double bonds. Okay, because if we look at this, if we just look at simply ethane, okay, and we compare it to ethene, which is that, the difference between the two, if we go from ethane to ethene, the difference between the two is that we've lost 2 hydrogen, and the reason we've lost 2 hydrogen is because we've got 1 carbon to carbon double bond. Okay, now because there's a difference of 4 hydrogens here, that must mean we have 2 carbon to carbon double bonds. Okay, I hope that makes sense. Now, if we go for, I'll go for another one, oleic acid. Again, this is another one that's got 17 carbons, but this time it's H33COOH. Now again, looking at that, yeah, you would expect it to be, if it was saturated, you expect it to be C17H35, but because it's 33, it's not 35, this is instantly unsaturated. Okay, and hopefully you should know, because there's 2 carbons less, it can, sorry, not 2 carbons, 2 hydrogens less, it contains only 1 carbon to carbon double bond. Yeah, where that one up there contains 2 carbon to carbon double bonds. And generally that's it. Okay, let's do more examples though, and then that'll be us. Now I don't actually have, well in fact no, I do actually. I've got one more fatty acid, which is behenic acid. Okay, and this is C221H43COOH. Okay, now is this going to be saturated or unsaturated. Okay, I want you to fill that in. Pause the video, okay, work it out, and then I'm going to go over the answer. Right, so this here, just by looking at it, I know straight away this is saturated. Yeah, and the reason it's saturated is it because it follows the CnH2n plus 1 COOH formula. Yeah, it's got 21 carbons, so N is 21. 21 times 2, 42, plus 1, 43. This is saturated. Yeah. Now, again, I've run out of acids. In fact, do I have any more? No, I don't. So I'm just going to have to make some up. So let's go for C16. H31 COOH, and let's go for C16. Oh no, let's not. Let's go change it. C20. H37 COOH. Okay. Now, what I would like you to do is tell me, is it saturated or unsaturated? And then as a sort of bonus, if you can tell me how many carbon to carbon double bonds there are. Okay, so I'd like you to pause the video, fill that in, and then unpause it because I'm just about to go over the answer. Now, if we look at this, I can instantly say this is unsaturated. Okay, the reason it's unsaturated, if we follow the general formula, maybe I'll do this a different pen. If we follow the general formula, that would be C16, H 2 times 16, 32, that would be H 33, COOH. So you'd expect that. However, because it's less, it's unsaturated. And because it's 2 hydrogens less, this means it contains 1 carbon to carbon double bond. Yeah? Now, this one, again, just looking at this, I can instantly say this is unsaturated. Okay, so hopefully you got that. Now the reason it's unsaturated is because if it was saturated, it would follow the general formula. So C20, N equals 20, so 20 times 2, 40, plus 1, that would be H41 COOH. Now, yeah, so it's less than the saturated formula, so it's unsaturated. Now, because there's 4 hydrogens left, there's 4 hydrogens less, this means it contains 2 carbon to carbon double bonds. So I hope that makes sense. Okay, next lesson on Thursday, I'll put up a starter. Okay, so make sure you understand, the key points to take from today's lesson is that fats and oils are esters, yeah, triglycerides. They're made up of 1 mole glycerol to 3 moles fatty acids. That's so important. Yeah, you need to know how to draw glycerol. Yeah, propan 1, 2, 3 trial. And you need to know that a fatty acid is a long-chained carboxylic acid. Okay, the fats and oils are made through condensation reactions. Okay, so 1 mole of glycerol reacts with 1, 2, 3 moles of fatty acids, and that causes us to get 3 ester links. Okay, so triglycerides, that's where that's coming from. And because we've lost 3 moles of water as well, you need to write that, yeah, 3H2O. Okay, now the next important thing you need to know, and this is probably the main thing you need to take from this, is why fats and oils why fats are solids, why oils are liquids. So fats are saturated, okay? They contain only carbon-to-carbon single bonds. This causes them to give a linear shape, yeah, which allows them to pack closer together and do a nice wee diagram, yeah. And because they're packed closer together, yeah, like that, the LDFs are stronger, harder to break, and that's why you're getting the higher melting point. That's why they're solid, yeah. And liquids are literally just the opposite, okay? They're unsaturated because they contain carbon-to-carbon double bonds. They cause kinks. These kinks cause the oil molecules to not pack closely together, and because of that, you're getting less LDFs, weaker LDFs, which are easier to break, and that means you're getting a lower melting point, and that is why oils are liquids. Okay, so important that. And then the next part you need to know that general formula for the fatty acids, CnH2n plus 1 COOH. Now that only applies to saturated carboxylic acids. Yeah, bear that in mind. That only applies to saturated fatty acids. If you have less hydrogens than the expected general formula, that means it's unsaturated. Okay, and for every 2 hydrogens you have less, that means that there's 1 carbon-to-carbon double bond. Okay, so I'll leave it there. Thank you very much.